Okay, here is the summary of what we have learned so far. We introduced U1 group, okay, which you know it's an abelian group. Let me go back and show you where it was. Somewhere here I think we wrote, yeah, here. So, e to the I theta, where theta is real, okay, and this satisfied all the properties. So, this one was the U1 group, okay, and it's abelian because all the elements of this group, they commute with each other. So, if you multiply element G1 with element G2, which are parameterized by the parameters theta, then the multiplication commutes. So, this is an abelian group, and we discussed other non-abelian groups such as SU2, SU3 and Lorentz group. Now, when we were looking at SU2 group, we introduced this group by studying 2 cross 2 unitary matrices with determinant 1. Okay. So, our starting point was these matrices, and then we found that these matrices form a group, and then we looked at the generators of the group by looking at the SU2 matrices in the vicinity of identity. Okay. So, we found that there are three generators T A, T B, T B, T A, T B, T C or T1, T2, T3, which are basically half of Pauli matrices. Okay. Then we looked at the set of 3 cross 3 unitary matrices with determinant 1, okay, and we found that that also forms a group, and that is called SU3, special unitary group, okay, and we found that it has 8 generators. And also recall that we started this entire thing by looking at Lorentz group, okay, which is basically a set of transformations which are given by this. So, if you start with x mu and go to x prime mu, the transformation is through these matrices lambda. Okay. And we also learned that this group, which is Lorentz group, has a subgroup which is the set of all elements which has determinant 1 and the lambda 0 0 element is greater than 1. And you saw that it has 6 generators. So, the generators were generically denoted by J mu nu, okay, but you know that it is antisymmetric under mu nu interchange. So, you have only 6 independent generators. Okay. So, that is what we had studied since till last time. Then we had also calculated the commutation relations which these generators satisfy. Okay. So, if you look at SU2 group, then the commutators, if I look at commutator T A with T B, it comes out to be I times epsilon A B C T C. Okay. There is a summation over C implied here, and your epsilon is Levi-Civita tensor, antisymmetric tensor. And if you look at SU3, similarly you can find the commutation relations, and I think I gave it as an exercise to find out all these constants. Okay. And note that I put the second index down here because this behaves differently compared to these two. So, on the left hand side, this object is antisymmetric under interchange of A and B indices, because if you put T B followed by T A here, okay, that is just negative of T A T B commutator. So, it gives you a minus sign when you interchange A and B, which is what we imply here by putting these two on the top. So, if the two indices on the top are antisymmetric under interchange of A B, but there is no such property implied here between interchange of B and C. So, that is why it has been put down to distinguish it from the status of these two. But of course, if you choose the generators to be such that they satisfy this normalization property which we were discussing last time, this one. Okay. So, you can choose a linear combination of these Hermitian traceless generators to be such that this property is true, then you can argue that this will be fully antisymmetric under ABC interchange, and in that case I will put the C up, okay, so that they all are having the same status. Also, we looked at Lorentz group, and here I have written down the commutation relation. So, as before, you have 6 independent generators. So, if I look at the commutation relations, I get this object. Okay. Now, the same commutation relation we had written down by defining new objects which have only one index. So, here J has 2 indices, here J has 1 index. So, clearly they are different objects. Okay. So, we introduced Ji's and Ki's. Ki's were the generators of rotation, boosts, and Ji's were the generators of rotation. Okay. And that these both objects are in J mu nu. So, if you write down this commutation relation here in terms of boost and rotation generators, you obtain the following. Okay. So, you see that if you look at Ji and Jj commutation relation, it gives you something which involves again a rotation generator. But if you look at the commutation relation of J and K, you have a K, but if you look at K with K, you get a J, a rotation. Okay. So, I mean this is happening because rotation forms a subgroup of Lorentz transformation, and that is what you see here. Okay. And these commutation relations are I mean the mathematical structure which is behind these commutation relations is what is called algebra. We will not go into giving the definitions of algebra, but for us it will suffice to say that these form the algebra of the Lorentz group or SU2 group or SU3 group. Okay, maybe I should say make a remark here. Okay, anyway, never mind. So, here it is good. Okay. Actually, what happened was I recorded this lecture and then I realized that the sound was not recorded. So, now I am redoing it. So, that is why the content is already written down. Okay, and I am sorry that this has to be done this way this time. Anyway, so let us revisit SU2. As I said, we were looking at 2 cross 2 unitary matrices with determinant 1. Okay. But if we were to forget about the fact that those matrices were 2 cross 2, okay, and just look at each matrix as an element, okay, and not really see the matrix there, then given 2 elements, you get a third element by multiplying. Okay. In that case, the multiplication is that of a 2 cross 2 matrix, but let us forget how you get it, but just see that given 2 elements, you get a third element. Okay. Now, suppose someone comes and gives you another set of matrices which is not 2 cross 2, but it is such that if you associate, so let us say that set has a the matrices in that set is n cross n. Okay, and the elements are labeled as G1, capital G1, capital G2, capital G3 and so forth. And here I have written down the matrices which are 2 cross 2, the SU2 matrices, and which I have written small g1, small g2 and small g3. And if it so happens that the multiplication here is identical to the multiplication there, okay, meaning if I take the corresponding capital G1, take the corresponding capital G2, and what I get is the corresponding G3, the one, okay, here. If it so happens, then this group, SU2 group defined through as 2 cross 2 matrices, will be the same group here, right, because the group is specified by telling what elements are there and what multiplying one element with another gives you. Okay, there is you don't need to tell exactly how it appears as a matrix, what is its matrix form, that we don't have to specify. Even without that, the group is specified, which means that this would also be another way to represent the same SU2 matrix, the same SU2 group, even though the matrices are n cross n, not 2 cross 2, where n could be different from 2, but they are talking about the same object, same group, SU2. Okay. So, right now we are not saying that 2 cross 2 matrices form SU2 group. We are saying 2 cross 2 matrices form one representation of SU2 group, but you could have different representations. Okay. Let me give you a specific example. So, there was a mistake here. So, construct the following matrices, which are 4 cross 4 matrices. Okay. So, right now GI, small gi's, they are 2 cross 2 matrices. Okay. So, I am imagining I have put a 2 cross 2 SU2 matrix here and the same 2 cross 2 SU2 matrix there, and put a 0 0 here. So, these zeros are basically 2 cross 2 matrices, 2 cross 2 null matrices. So, this entire matrix is 4 cross 4, and if I were to multiply this with this matrix, where again I have put 2 cross 2 matrices here and 2 cross 2 matrices here, then you can see that what you will get is this. Okay. And if you see that these matrices, they satisfy exactly the same multiplication as you had for SU2, right, because really the multiplication is happening between these blocks, right. So, it is not a surprise that what multiplication you are getting is identical to what you had for 2 cross 2. So, if you were to look at these matrices, okay, these 4 cross 4 matrices, they would be satisfying exactly the same SU2 group multiplication rule. Okay. So, we can say that these matrices form a representation of SU2. Okay. So, as I was talking about here, this is a particular example of one representation of SU2, which is not 2 cross 2, but 4 cross 4. Okay. That is what I have written here. This is a 4 cross 4 representation of SU2. So, what is that 2 here in SU2? Clearly does not mean that you are looking at 2 cross 2 matrices. What it means is that the way you have discovered this group is by looking at 2 cross 2 unitary matrices. So, we call that 2 cross 2 representation, because now we can have representations of different dimensions. So, the 2 cross 2 is also a representation, and we call it defining representation, because that is the representation that you use to define SU2 group. So, it is called a defining representation of SU2. Okay. And that is what I have written here. 2 cross 2 representation is defining representation of SU2. You can think of many more. So, here is another very simple example. You can put blocks like this. Again, this will be obviously following the multiplication of SU2. So, in general, we say a representation R for SU2 or any group. Okay. So, R is the symbol we use for specifying the representation. So, if you look an element Gi of a given group, okay, in representation R, then it corresponds to the matrices which are represented by this. Okay. So, dr is the matrix representation in the representation R of the element G. Okay. So, this is some matrix, okay, and these matrices will change, the dimensionality of them will change, and elements of them will differ depending on the representation R you are looking at. Okay. So, of course, there is one variety of representation that we have already talked about, which is of this form. So, if I look at a representation R, and if I look at the elements Gi and their corresponding matrices. So, this is the matrix corresponding to the element Gi in representation R, then it would be, then it could be in this form, where you have the matrix in representation R1. So, that is put in one block, then you have these null matrices here, and then you have the element Gi, and sorry, it should not have been here, it should have been here, but in representation R2, okay, where R1 is different from R2, you can take it to be different. So, these matrices are from another representation, and if you put them together like this in a block, in these two blocks in this matrix, that will also form a representation, because when you multiply such matrices, the multiplication will happen in the respective blocks, okay. And because these form a representation, this entire thing will also form a representation. Okay, and if you are able to write any representation in this form, where you have such blocks, it is called reducible representation. Okay, it is reducible because the real thing is in here or in here. Okay, and if you cannot write a representation in this form as blocks here, then it is called irreducible. Okay, and of course, it would be interesting to know all the irreducible representations of a group, because once you know all the irreducible representations of a group, you can construct all other remaining reducible ones, because you just have to put blocks like this, okay, whichever way you like. And of course, the 2 cross 2 matrices of SU2, they are irreducible representations, because they do not have this structure. Okay. Okay. Now, I want to talk about we go back to our this Lorentz transformations. Okay. So, we were looking at all the transformations which keep this unchanged, okay, and we found that the most general solution was this, that x prime is lambda mu nu x nu plus a mu, where a mu is constant, and we also talked about the fact that these a mu's are the translations. So, they generate time translations and space translations. Okay. So, if you took lambda to be identity, meaning you are not doing any Lorentz transformation, then it is x prime is x plus a mu. So, it is just shifting the values of x. Okay. And we have already seen that Lorentz transformations form a group. So, if you look at all the matrices lambda mu nu and the corresponding transformations here, then they form a group. Okay. And then we have translation group. So, if you take these transformations x prime mu is x mu plus a mu, you can easily verify that these transformations form a group. Okay, because of you have to check the closure, inverse and everything, and identity, and it will be very easy to verify that translations do form a group. And these two transformations together is what constitutes Poincare transformations. So, here what you have is Poincare transformation. Okay. So, if you exclude the translations, then you have only Lorentz transformations. If you include translations and have both Lorentz transformation and translation, then you call Poincare transformations. Now, you may wonder whether Poincare transformations form a group, and indeed they do, and here is how to find it. So, suppose you start with a space time point x and do a Poincare transformation, which is parameterized by a lambda and a, okay, where a is constant, and of course, this is also constant matrix. Okay. So, you do a transformation on X and go to X prime, okay, through and the transformations are parameterized by lambda 1 and a1, and this is exactly the transformation that you have. And once you have reached X prime, you do another transformation which is now parameterized by lambda 2 and a2, and you reach some X double prime. So how do I verify that these transformations form a group? What I should do is do this followed by that, and whatever I get, I should be able to put it in this form. Whatever I get, I should be able to say that it is a Lorentz transformation acting on X followed by a translation. If I can say so, then I would have proved that Poincare transformations form a group. Okay, so that's what we are doing here. So X goes to X prime. So X prime rho is lambda 1 rho sigma X sigma, that's this part here, plus a1 rho. Okay, that's the translation part. Now once I have reached here, I do the second transformation on this object, and now with lambda 2 a2. So X double prime mu is, what is there here, lambda 2 mu sigma acting on X prime. And what is X prime? X prime is this, right? So I put it here, lambda 1 rho sigma X sigma plus a1 rho, plus a transformation, translation transformation, plus a2. So I should write a2 mu. Okay. Now this is, I can write as lambda 2 lambda 1 x. So that's what I write here, lambda 2 lambda 1 x, and let's see whether all the indices are fine. Sigma is contracted, so that's not an index, free, not a free index. Rho is contracted, it's not a free index. Only mu is a free index, which is on the left hand side, so that is good. Here rho is contracted, only mu is free, so that is also good, and I have mu here. Okay, so let us call this last two terms together as b mu. See, these are constants, right? There is no piece, there is no x in this part, there is no x mu in this part, x is only in this part. So as far as translation is concerned, I have a translation. You see, the translation part is not multiplied with x, translation part sits separately. So that's the part here, that's the translation. Now let's look at this part. This part has two lambdas, unlike a lambda here, but that's not an issue because we know that Lorentz transformations form a group, meaning one lambda followed by another, the multiplication of two lambdas is again another lambda because it's a group, right? So lambda 1 times lambda 2 will be some lambda within the group. So these two together is some lambda, which means what we have here has exactly the same form here. Okay. Thus, we have proved that Poincare transformations form a group. Okay. So if I write down the elements of Poincare group like this, so I say that there are two pieces to it. One is the translation part, the one element is one parameter is translation, actually these are four parameters, not one, and another is lambda. Okay. Then if I take one transformation which is parameterized by a1 lambda 1 followed by the another one which is a2 lambda 2. So I am imagining I am doing a transformation on some x here, okay, some x here, first by this and then by that. Then what I get is this piece. Okay, let us go back and check how do I get this. So here x double prime is exactly what I was writing on the next page, and the answer is that you get a2 plus lambda 2 a1, a2 plus lambda 2 a1 page. Okay. A2 lambda 2 A1. So, that is the translation you have, and this one was of course lambda 1 times lambda 2. Okay, and you would like to know the generators of Poincare group and what is the algebra of Poincare group. So, we would want to know algebra of Poincare group. Okay. So, what are the generators of translations and how do they commute with themselves and Lorentz transformations? Okay. So, that is what we want to know, and that is what we will take up in the next video. But the reason why these commutation relations are important is because once you know these commutators, you can construct finite transformations, and these commutators are the only thing that you know, that you need to know. Okay. So, if we know the commutators, meaning the algebra, then we can construct the finite elements of the group. Oops. Okay. And you do not need to know anything more than the commutators. So, you do not have to know, for example, commutator with several. So, you do not need to know something like this. For example, let us say K I J I, okay, and something here, let us say again K I. Do not need to know these kind of objects. Just knowing the commutators is it's sufficient. So, once you know the commutation relations with two generators, they will give you all the elements which are connected to the identity. Okay. See, there may be parts of the group which cannot be generated by knowing only the generators of the algebra, right? Because, for example, you remember in Lorentz transformations you also have parity and time reversal, and those things you will not get by using the rotation and boost generators. They cannot produce parity transformation, but you will be able to produce all the elements of the group which are connected to identity by using the generators. Okay. So, that is why the algebra is important, and we will look at the Poincare group and its algebra in the next video.